Hi everyone, welcome back to the Heterogeneous Parallel Programming class. This is lecture 3.6 and we're going to be working on data reuse benefit analysis in tiled convolution algorithms. The objective of this lecture is for you to learn how to analyze the benefit of tiled parallel convolution algorithms. And in the convolution computation, the reuse pattern is more complicated than matrix multiplication, and mainly because the access patterns are less uniform across threads compared to matrix multiplication. And so this is a more complex analysis, as we will see in the lecture. But it's also a very important pattern because this type of analysis will be directly applicable to stencil type computation in partial differential equation solvers and so on. So it is a very important foundation for analyzing memory data access benefit of tiled algorithms for many types of computation. So here we show a small 8-element output tile example in the 1D convolution. So we show the tile from element 8 to element 15. And we still assume that the mask width is 5. So if you recall from the previous lecture, the input tile need to have 2 more elements on each side. So we're going to have 12 elements in the input tile. And the next few slides will be based on this particular configuration. In order to load the input tile, we need to load 12 elements into the shared memory. So that's the total number of memory accesses we need in order to bring all the data that we need in order to calculate the output tile elements. And here we show a very simple way of calculating the total number of memory accesses that are to the global memory that are replaced by shared memory accesses. Without tiled algorithm, without using shared memory, the calculation of every output element is going to require 5 input elements. So we see that element 8 is going to require elements 6 through 10 in the input array. And then the calculation of output element 9 is going to require element 7 through element 11. So as we can see, every output element is going to require global memory access of 5 input elements. So this leads to the conclusion that we're going to need to have 8 times 5 memory accesses if we did not have the input tile in the shared memory. So this gives us the following simple calculation of the benefits. We spent 12 memory accesses to load the input tiles. And as a result, we're able to convert 8 times 5, 8 output elements and 5 input element access each, 14 of global memory accesses into shared memory accesses. And these accesses were replaced by shared memory. So the total number of global memory accesses before the tile algorithm is 40 accesses, and the total global memory accesses with the tile algorithm is 12 accesses. So the reduction of memory bandwidth requirement is 40 over 12 and 3.3. So we actually magnified. Another way of looking at it is that we magnified the memory bandwidth by 3.3 times, or we can say that we reduced the total number of memory accesses by 3.3 times. In general, if we have a output tile width, in the previous example, the output tile width is 8, and then a mask width, in the previous example, the mask width is 5. And the general formula for calculating the total number of input elements loaded for an input tile is the output tile width plus the mask width minus 1. So that's really just the input tile width. And this gives us the total number of global memory accesses required for a arbitrary input tile. And then for the global memory accesses without tiled algorithm will be the number of elements in the output tile, which is output tile width times the mask width, because every output element is going to require a mask width number of input elements. So we can calculate the reduction of memory accesses as the total number of accesses without the tile algorithm, which is the output tile width times mask width divided by the total number of memory accesses for loading the input tile, which is output tile width plus mask width minus 1. And this gives us the general formula for any output mask, output width, and mask width combination. And we will see that we can actually calculate this number for some of these different variations and get some additional insight into the savings that we can have for 1D tiled convolution. And one thing that I do want to remind you is that this particular calculation ignores the effect of ghost elements in the edge tiles. So in general, when we do a quick calculation of savings or reduction in memory accesses, as long as the tile width, output tile width is reasonably large, we can actually ignore the effect of edge tiles. On the other hand, if we really wanted to, I leave it as a homework for you to calculate the actual savings for those tiles that are at the edge of the images. And in particular, you should assume that when loading the input tile, you don't need to go access global memory for the ghost elements, but also in the calculation of total global memory accesses without tile algorithm, those elements also don't need to be loaded from the global memory. So when you calculate the ratio, there will be somewhat of a change, but it will not be a whole lot as long as the output tile width is reasonably large. There's actually another way to calculate exactly the same reduction ratio, memory access reduction ratio. So we can actually calculate it from the input elements perspective. The previous calculation uses output element perspective. So here we can calculate the number of reuses that we have for each input element that we load into the shared memory. So for example, when we load the element 6 into the shared memory, only one thread is going to use the element to calculate element 8 in the output. On the other hand, element 7 is going to be reused twice. Once to calculate element 8 and once to calculate element 9 in the output. So we can enumerate the number of uses of each input element that we load into the shared memory. So if we continue this enumeration, we see that element 9 in the input is going to be used to calculate element 8, 9, 10, and 11. So 9 is going to be reused 4 times. And then we go into a section where elements 10, 11, 12, 13 are all going to be used 5 times to calculate 5 of the output elements. And I leave that up to you, but I give you one example of 10 here. So, but once we finish 13, we go into a decline again. Element 14 is only going to be used by the calculation of 4 elements, meaning output elements 12 through 15. And then element 15 is going to be used 3 times, and element 16 is going to be used 2 times, and element 17 will be only used 1 time, basically to calculate the output element 15. So you can see that this is a increasing series, and then there's a kind of a plateau, and then there's a decreasing series. So we can calculate the total number of global memory accesses that that would have been made for the input elements but converted into shared memory accesses by calculating these uses of the input element by the calculation of the output. So we can add up all these uses of the input element, and this gives us 1 plus 2 plus 3 and so on. And then there's 4 of those elements that will have 5 reuses, and then we have the decreasing series again. We add up all these numbers, we get 40, and then the total number of memory loads that we need to load the input tile is still 12. So we take 40 and divide it by 12, we get 3.3. So this gives us exactly the same number. And this shows that you can have multiple ways of calculating the total number of global memory accesses that needs to be made without a tiled algorithm. And then you can divide it by the total number of memory access needed to load the tile into the shared memory. And then you can do the division. And even though we did it for output element perspective and input element perspective, we come up with the same answer, which is a good thing. In general, for one-dimensional convolution, we can calculate the input-oriented reuse by listing the reuse of all the elements in the input tile. So we will start with 1, and then we will have an increase into mask underscore width minus 1. And after that, we will have a section of elements that will be used by mask width times. So the section width, the number of elements in that section is actually the output tile width minus mask width plus 1. And you can go back and verify this in general. And after a while, we go into the decreasing series. We start with mask width minus 1 and then go all the way down to 1. So for mask width, larger values of mask width, the increasing and decreasing series is going to be longer, and the middle section is going to be shorter. But for smaller mask width, the increasing and decreasing series will be shorter, and the middle section will be longer. And if we look at these series, we see that the increasing series and decreasing series are symmetric. So we can just do a pairwise addition. So the first element of the increasing series and the first element of the decreasing series add up to mask width. And then the second element of the increasing series and the second element of the decreasing series also add up to mask width. And they're mask width minus 1 of them. So this gives us a sum of mask width times mask width minus 1. And this is just a classical way of summing up a increasing and decreasing series. So then the middle section remains as the second one, mask width times the output tile width plus mask width plus 1. Now both terms have a common mask width term, so we can factor it out, and then we can add up the other two terms, and this gives us output width period. So this gives us a total of mask width times the output tile width. And so this is a very simple calculation, but this gives us the total number of global memory accesses that are, that are converted into accesses into shared memory shared memory version of the input tile. And we still will need to spend output tile width plus mask width minus 1 memory accesses to load the input tile. So we can calculate the ratio of the two, which gives us the number, the savings, and we will come back to this point in a few slides. Actually, in this slide. So here are some examples of bandwidth reduction for some combinations of the output tile width and the mask width. So in the horizontal direction, we list some different output tile width. So 16, 32, 64, 128, and 256. And then on the vertical direction, we show two different mask width. One is 5 and one is 9. And as we can see, if we plug in these numbers into this reduction formula, ratio formula, we see that as we increase the output tile width, the ratio increases towards 5. And this is actually intuitive, because ideally every output element will be using 5 input elements. So the reason why we don't have 5 times reuse is because we have some of the elements on each side of the output tile that are using the elements that will be reused fewer times, because the input tile is bigger than the output tile. And if we use a bigger mask width, then we would also start with a smaller value, and then we'll increase towards number 9. But as you can see, when we use a bigger mask width, even when we get to 256 elements in the tile, we're going to be more sort of the difference between the actual reuse and the ideal reuse is actually a little bit bigger, because the input tile needs to be more bigger, much bigger than the input tile of the case for mask width 5. And so this demonstrates an interesting fact. That is, whenever we have a tiled convolution, we would like to have a reasonably large output tile width, so that we can actually have a reasonably good reduction, memory bandwidth reduction ratio as a result. And this tile needs to be even bigger if the mask width is wider. So this motivates the use of bigger tile sizes and the bigger block sizes and so on. Now we can go to the two-dimensional case. For your machine problem assignment, you're going to be doing a two-dimensional convolution. And we can apply the analysis that we did for the one-dimensional case in a very straightforward way. So we can calculate it as the input tile. So we will need to have output tile width plus mask width minus 1 width for the input tiles. So if we take the square of that, that gives us the total number of input elements that need to be loaded into the shared memory. So this is the memory accesses that we still need to do after with the tile algorithm. And then if we look at the calculation of every output element needs to access the input mask width squared input elements. So essentially, it's that neighborhood of input elements. And then there are output tile width square number of output elements that we need to calculate. So the total number of global memory accesses that are being converted into shared memory accesses is output tile width square times mask width square. So overall, the memory access reduction ratio is going to be exactly the output width square times mask width square divided by output tile width plus mask width minus 1 squared. And you should be able to expect that the reduction is going to be more significant than the one-dimensional case. So if we look at some concrete numbers, here we show the tile width from 8 to 64, and then the mask width from 5 to 9. And remember, because we're talking about squared, the reuse is going to approach 5 squared, which is 25. So when we get to 64 by 64, we'll have 22.1 reuse memory access reduction. And if we use 9, when we approach 64 by 64 output tiles, we're going to have a ratio of 16, not quite the 81 that we would like to see in an ideal case. However, for this 2D convolution, there's something more subtle in the analysis. If you look at the tile width, and remember, tile width plus mask width minus 1 gives you the input tile width in our kernel, it's going to be the size, essentially the width of our blocks. So if we have a 16 output tile width, that gives us 20 threads on each side. So it gives us 400 threads in the block. So this already requires 400 threads in the thread block. And if we use 32 output width, then it gives us 36 times 36 threads in the thread block, which already exceeded the maximal number of threads we can have in each thread block included. So even though the 19.7 and 22.1 numbers are kind of interesting, they're not practical. We will not be able to use those numbers for our kernel. So our kernel is going to operate more in the 16 by 16 realm. In fact, a good number is going to be 12 by 12 for the output tile and 16 by 16 as for the input tiles. And that will give us somewhat less than 16 times reduction for the 5 mask width of 5. And another consideration is that in general, because we need to do barrier synchronization, we will need to be able to have multiple thread blocks. Well, one of the thread blocks is doing barrier synchronization. Another thread block can actually make progress. So this also argues for something closer to the 16 tile width, because this leaves room for multiple thread blocks in an SM. And we could do a similar calculation for mask width of 9. And here we see that for a 16 by 16 output tile, we will be able to get somewhere around 36 times memory reduction. So these numbers are actually quite significant. They are quite similar to the matrix multiplication reduction ratios. So for convolution, if we use in the lab, if we end up using a 12 by 12 output tile, 16 by 16 input tile, we're going to get somewhere around between 10 and 12 or so reduction in the memory access. And that's a fairly reasonable number, but not quite as good as what we like to see, in the ideal case. So this brings us to the end of the lecture. And you should be ready to answer some of the questions that we have for the machine problem assignment. And the skills that you learn here is a very important skill. Essentially, this is the kind of discrete mathematics analysis that we often use to analyze the execution behavior or the benefit of certain types of algorithms in a parallel execution environment. So we will still see a couple other types of analysis that are commonly used for analyzing the benefit of these techniques. So we don't have any additional reading in the textbook. So I'd like to encourage you to finish the machine problem of convolution, two-dimensional tile convolution. Thank you.